Okay, so this week we're going to continue with FTC, Fundamental Theorem of Calculus, Part 1 and Part 2. Just a note, in the notes that we did last time, for that Part 1, so I called Part 1, in your tutorial the question says Part 2. So like I said in the lecture, if you're looking at the notes, the tutorials, or anything online, sometimes it mixes up Part 1 and Part 2. Okay, but you should be able to see from the question which one's which. In the test, I'm not going to say Part 1 or Part 2, I'm just going to give you the question and you need to know which one to use. Okay, so when you're doing your work at home, just remember Part 1 and Part 2, it might be swapped depending on where you look. Okay, but again, the question will make it very clear what you need to do. Okay, so a quick recap on Part 1. Okay, so this is what I'm calling Part 1. Other notes or online might call it something else. Just make a note. So if you've already written notes using some other website or so on, just make a note which one's which for you. Okay, so Part 1 was a new method for calculating definite integrals. So we have the integral from a to b, f of x dx. We know what all of that means now. This is given by any antiderivative evaluated at b minus any antiderivative evaluated at a. Okay, and last time we went through that issue of if it's any antiderivative, will that mess anything up? And we showed that it doesn't, because any plus c you put on this first term gets cancelled out with the minus c that you have with the second term. So any constant doesn't matter, we're just going to treat it as 0. Okay, so that plus c we had for those antiderivatives, we don't need to worry about that here. Okay, so with this in mind, this integral from a to b equals this antiderivative at b minus antiderivative at a. We're going to use this to redefine the notation for antiderivatives. So remember, we had this function little f of x, and we found the antiderivative capital F of x. Okay, so we did this a little while ago, and we used this notation of capital letter. So if you have a little function f, then capital F was the antiderivative. That's like what we're using over here, okay, with this capital F there. If you have a little function g, the antiderivative is capital G. So now we're going to redefine this. So this capital F of x, it's just another notation, it's nothing new here. We write this as the integral f of x dx, but we don't put the bounds. Okay, we call this an indefinite integral. Indefinite integral. Previously we called it the antiderivative. Okay, so it's just a little bit of notation there. So for the definite integral, we have the bounds from a to b, and this right-hand side, when you fully evaluate it, that's a number, right? A definite number that you can write down. For this antiderivative notation, see, we don't have any lower bounds, we don't have any upper bounds, we leave those out. So what this is just the antiderivative. No evaluation at the upper bound or lower bound. Okay, we call that the indefinite integral. Okay, so that's just another bit of notation that you might see for the antiderivative. Okay, and of course we can put the plus c so we don't forget that. I saw in the quiz a number of students were leaving out the plus c. If you leave out the plus c, you're going to get half instead of 1 for that. Okay, this plus c is very important to put down. Okay, so all of this here is just some new notation. So if I say indefinite integral or antiderivative, we know that they mean the same thing. Okay, let's go through a few more examples before we start on the new work. Okay. Okay, so let's say we have the integral from 0 to pi sine x dx. Okay, and I had a few students asking me at the end about this pi here. This pi is the same pi that we used with the radians. Okay, so whenever you have a trig function and bounds, we treat the bounds like any angle, okay, because it's a trig function, and it's in radians. So please make sure when you are doing that evaluation that your calculator is set to radians, not degrees. I saw in the past test, a few students had it in degrees mode, and then your answer's off. Okay. Now I can tell if it's in radians or degrees, so I can give you part marks because I know what you're doing. However, your final answer's wrong. Okay. So please make sure that if you have anything with pi, pi over 2, pi over 4, anything like that with trig functions, that your calculator is in radians mode, not degrees. Okay, so please just keep that in mind for the upcoming assessments. Okay, so we need to find the integral. So here we need to find the antiderivative of sine. What is that going to be? Minus cos, good. So we have minus cos x from 0 to pi. So you can put your antiderivative here in square brackets like this. That's what I use. That's what's going to be in the solutions. However, if you're looking at this online, you might see it as minus cos x vertical line 0 to pi. Means exactly the same thing. It's just different ways of writing it down. Both are fine. Okay, I'm not too worried which notation you use. Okay, so now we evaluate this at the upper bound minus evaluating it at the lower bound. Whenever you have a minus here with your integrand, it's best to put everything in brackets so you don't make a sign mistake. So we're going to have brackets and then cos pi minus and then brackets minus cos 0. Okay, so the brackets just helps us keep track of all these minus signs here. Because if we have minus minus, that's going to be a plus. If you forget the brackets, you might just put one minus sign down, and then everything's wrong after that point. Okay, cos of pi, that's minus 1, so minus minus 1, that's going to be a plus 1. Cos of 0 is 1, and again we have a minus and a minus, so that will be a plus 1. So that's going to be a 2. Okay, and again, if you have a minus and a minus, please check your signs there. Okay, another example, let's say we have the integral from 0 to 1, x squared plus 3x cubed plus 1. Okay, polynomial, we know what to do with polynomials. We look at each term individually, because we know we can do that from the definite integrals property. We look at each exponent, we add 1 first and then divide. It's always the opposite of what we did with derivatives. So derivatives, we minused 1 and then multiplied. Going down, here we add 1 and then divide. Okay, so again, square brackets, we need to put the antiderivative, add 1 to make it 3, divide makes it a third, so we have 1/3 x cubed, plus add 1 to make it a 4, divide, so we get 3 over 4, x to the 4. And here, there's no exponents to add or anything, but we know that it should be x because the derivative of x is 1. So if you ever forget your rules, think about what do I need to differentiate to get back to this. So I've got a 1. What do I need to differentiate to get back to 1? X. So it's x. From 0 to 1. Okay. Now, quick check here. If the bottom bit is 0, we see if we substitute 0 here, all of it's going to be 0, so we don't have to worry about that. If we substitute 1, we're going to get 1/3 plus 3/4 plus 1, and then it's going to be minus 0. Okay, but we saw that it's all going to be 0, so you don't need to write that down. Okay, so any time that you can save by quickly checking what it should be, please do that. Okay, so don't write everything out if you know it's going to be 0. Okay, if you're not so comfortable with that and you do want to write everything out, please do that. Okay, but if you're comfortable with it, try to save some time and, leave out unnecessary things. Okay, so this will be 1/3 plus 3/4 plus 1. Don't worry about the 0. Okay, you've got your calculators, just add that up and you get your final answer. Okay, let's do one more. So we have the integral from 1 to 2, x plus 1 over x dx. Okay, now you might think this 1 over x, you might want to write it as x to the minus 1. Please do not do that. Remember, this was a special case that we looked at. If it's 1 over x squared, we can write it as x to the minus 2. If it's 1 over x cubed, we can write it as x to the minus 3. Those are fine. X to the minus 1, we don't use the power rule. Okay, remember we had that table, and I put a big star there to say that was an exception to the rule. So we leave it as 1 over x. Do not write it as x to the minus 1. Okay, but for the first term, we can have x to the 1. We add 1 and divide. So it will be 1/2 x squared plus the natural log absolute value x. Okay, so in the quiz, a lot of students didn't put the absolute value. I still gave you the mark. That's fine for that part. But from now on, please make sure that you put the absolute value of x. This is important here because when we have these definite integrals, we're going to be substituting values. Sometimes those values will be negative, and you can't take the natural log of a negative. So here, let's say we went from minus 2 to 2. Here you would be putting in minus 2, and on your calculator, if you put log of minus 2, you're going to get big problems. Okay, please make sure you put the absolute values. Okay, from 1 to 2. So here, it's not going to make an issue, but they do still need to be there. Okay, so this will be half of 4, so 2 plus the natural log of 2. Now we can drop the absolute value because we know it's positive, no problems there. If you want to keep the absolute value just to be safe, that's perfectly fine as well. Okay, minus 1/2, and then the log of 1 is 0, so we don't need to put that down. Okay, and again, you can leave your answer like this, or you can put it in your calculator to get a decimal. Okay, that's up to you. All right, any questions so far? Okay, so it's always the same 3 steps. You find the antiderivative, okay, that's step 1. You substitute your upper and lower bounds, so f at b minus f at a, please don't swap them around. And lastly, you simplify if you can. Right, any issues with this? Okay, just a side note, please go over your trig functions, your derivatives and antiderivatives. So I'll just put that as a note. Those that have done the tutorial, you'll see there's those trig functions there. So sine, cos, tan, sec, cosec, cotan. Okay, so those basic ones, derivatives and antiderivatives, as well as sec squared. We did that one previously. Remember, the derivative of tan is sec squared, antiderivative of sec squared is tan. It always goes back and forth. But the one that we didn't do was cosec squared. Very similar to sec squared, it's going to be minus cotan. So whenever you're going between the trig functions and their cofunctions, there's usually a minus sign involved. Okay, so here with the cosec squared, you'll get minus cotan. Okay, but please just check that. Also, sec x tan x and its co-partner cosec cotan. Okay, so these will come up. If you're not familiar with these trig functions, especially the co ones, so the cosec and the cotan, and so on, please go over those. The derivatives and the antiderivatives. So just make that table. So you got the one side, you differentiate, you go to this side, you anti-differentiate, you go back. Okay, just make a note of that. They do come up quite a bit. Okay, let's put down the homework. Okay, so the previous, not the previous homework, the one before, was proving those properties of the definite integral. and we proved them using the limit of a Riemann sum. Okay, so we had the integral from a to a, for example. We used the limit of a Riemann sum and we got 0. Okay, now we're going to redo all of those, but using this definition here. This one here with the antiderivative. Okay, so all those properties we had before, like going from a to a will give you 0, or going from b to a will be minus the integral from a to b. All of those can be proved using this definition as well. Okay, so that will be for homework. Okay, so I'll just put the note here. So integral from a to b, f of x dx is equal to f at b minus f at a. So we're going to use this as our starting point. And then the things to prove, integral from a to a, f of x dx is equal to 0. You should have these before, but I'll just rewrite them. Integral from a to b, f of x dx is equal to minus the integral from b to a, f of x dx. Okay, number 3, integral from minus a to a, f of x dx is equal to 0 if f is odd. The integral from minus a to a, f of x dx is equal to twice the integral from 0 to a, f of x dx if f is even. Okay, number 4, the integral from a to b, k times f of x dx, so that's taking the constant out. So that will be k times integral from a to b, f of x dx. Okay, and number 5, integral from a to c, f of x dx is equal to the integral from a to b. So this is where we split up the big interval into sub-intervals. So instead of going from a to c, we go from a to b, and then from b to c. Plus the integral from b to c, f of x dx. Okay, so these 5, that will be for homework. Okay, so when you're submitting the homework, you don't have to do all of them. If you show me that you've only done 2 of them, then you'll get the points for the 2. If you show me that you've done all of them, then you get the points for all of them. Remember, it's first come, first serve. So please be quick about it if you want those points. Okay, and then these, it won't be in the test, but it might be in the quiz. Okay, these proofs. All right, any questions on that? Okay. Okay, so that was FTC 1. You should have had plenty of practice with that with the last tutorial. Now we're going to look at FTC 2, which appears in this week's tutorial. And again, this might be labeled differently to what you see in other notes. Okay, so we won't go through the proof. I will provide it in the notes, but okay, we won't go through it in class. You can read that yourself. Okay, so given a function g, and it's defined like g of x is equal to the integral from a to x f of t dt. So here the function is defined in terms of an integral. Okay, so this will be important for the assignment. Hint, hint. Okay, so this is a pretty complicated looking function. Okay, it's not like a normal polynomial or rational function or anything like that. This is defined in terms of an integral. This is used quite a lot in math, physics, and engineering, you will see these things come up later on in your studies. Okay, just as a few examples, we have this function called the sine integral, and that's the integral from 0 to x sine t over t dt. This is used quite a lot in engineering. Okay, we won't go through this specifically, but it's just an example of what you might see come up. Okay, there are other ones, like the cosine integral, 0 to x 1 minus cos t over t dt. And again, that shows up in math, physics, and engineering. Okay, so sometimes when you're writing out functions, you may not be able to write them so neatly. Sometimes this is the only way that you can write them, okay, as an integral. Now, with these things, we still want to do calculus with them. For example, we want to take the derivative. But if it's written in terms of an integral, how do we take the derivative? Okay, to do that, we use this FTC part 2. Okay, so FTC2 tells us that if we have this function, okay, g of x, integral from a, which is some constant, to x, f of t dt, then g prime, which we can write as the derivative of the integral, is just the integrand. Remember, that's our function in the middle, f at x. Okay, that is the fundamental theorem of calculus part 2. So this again relates our integral calculus to differential calculus. So just to summarize again, with FTC1, we saw that the integral can be written using an antiderivative. So that relates integration and differentiation. FTC2 also does that, and it shows us that differentiation and integration you can think of as opposites. So here we've got this function f of t, we're integrating it, and then we're differentiating it, and we get the function back. Okay, so they're kind of like inverses. Okay, so if you integrate the function and then differentiate the function, we get the function back. Okay, so that's how you should be thinking about this FTC2. Okay, let's look at a few simple examples, and then we'll move on to the more complicated cases. Okay, so let's say we have the function g of x. That's the integral from 1 to x, 1 over 1 plus t squared dt. Okay, now with this one, we could evaluate this and write it out as a function, because we know that the derivative of arctan is arctan x is 1 over 1 plus x squared. Okay, we've done that before. So here, this antiderivative would be arctan. So we could take arctan evaluated at x minus arctan evaluated at 1. Okay, so you could do that. However, here, if we just want to find the derivative, we don't need to go through all that work. What we could do is just use FTC2. So here we have g prime. That is the derivative of the integral. Okay, we're not going to evaluate the integral. FTC2 tells us that it's just going to be the integrand evaluated at this value x. So it will be 1 over 1 plus x squared. Yeah, so no need to take the antiderivative. However, in this case, we could have done that. Okay, let's look at another example. G of x is equal to the integral from x to 1, the natural log of 1 plus t squared dt. This one is a bit more complicated for two reasons. The first one is that this integrand is a bit more complicated. In this case, we can't find the antiderivative easily. In this previous one, we could have written this as arctan and then done the derivative. Here, we can't find the antiderivative. It's too complicated. Okay, so that's the first reason. Yeah?
confused why using T.
Oh, t. So we're using t because x appears in the bounds. So we can't use the same variable for both. Okay. So it's just a renaming so that this x, so we can put x here. This can't be x as well. Okay. Okay, so first reason, the integrand's too complicated. Second reason, x is at the bottom. So if we go back to this FTC2, FTC2 had the x at the top. We need to be very careful about these things. X is at the top. In our problem, x is at the bottom. That's an issue. So to get this in the correct form, we need to have x at the top. If x is at the bottom, we want it at the top, we need to swap the bounds. If we swap the bounds, we get a minus sign. Okay, that was one of those properties. So this was minus integral from 1 to x, the natural log 1 plus t squared dt. Okay, that was our definite integral property that we used. Now we can use FTC2 because x is at the top. Okay, so g prime is going to be the derivative, the minus 1 we can take out, so it can be minus d by dx, the integral from 1 to x, the natural log of 1 plus t squared dt. Okay, again, the derivative and the integral, they cancel out, so it's going to be minus the natural log 1 plus x squared. Okay, we take our integrand and we evaluate it at x. Okay, and we get the minus sign because we had to swap the bounds because that's what we need for FTC2. Okay, a few more examples. G of x is equal to the integral minus 1 to x, 1 plus t squared plus cos t, x plus 1, cos t dt. Okay. Again, a little bit more complicated because in the top here we have x plus 1. FTC part 2 says that the top part needs to be just x. Here we have x plus 1, not going to work. So to get this looking like what we want, we're going to make a substitution. So substitute u is equal to x plus 1. Right, that's the easiest way to make that top part a single variable. We just call it a new variable and that bit's done. So now, it's not going to be g of x, we can write this as g of u of x. Integral from minus 1 to u, 1 plus t squared plus cos t dt. Okay, so we've done a little substitution there where we've replaced that upper bound with a single variable. Now we want to take the derivative with respect to x. That's still the goal. We may have changed the upper bound to u, but we're still trying to differentiate with respect to x. It may be a bit easier to see on the other side. We have g of u of x. If we're taking the derivative with respect to x, we need the chain rule. So we differentiate with respect to u and then multiply it by du by dx. Right, just the chain rule. So d by dx of g, that's going to be dg by du, du by dx. That's the chain rule. Okay, so we're just using the chain rule. Okay, that's because we introduced this u variable. So g is in terms of u is in terms of x. If we're differentiating with respect to x, we need to follow the chain rule accordingly. Okay, dg by du, so we're differentiating this right-hand side with respect to u. That's easy to do. FTC part 2, we're good. Because this top part is a single variable, we can take the derivative quite easily. So, FTC part 2, we take the integrand, and we substitute that upper bound, which is u. So it will be 1 plus u squared plus cos of u. Okay, quite easy to do there. Then, chain rule, du by dx. U is equal to x plus 1. Taking the derivative, we just get 1. Okay, but we're not done yet, because here we still have this u variable. Remember, we put that in. Okay, that's not part of the question. So to go back to the x variable, we need to replace u with x plus 1. So our final answer will be 1 plus x plus 1. We've substituted, and then cos of x plus 1. Okay, so remember that u is just a middle step. It's not the final answer. We introduce u to allow us to use that FTC2, but once we've done all of that, we need to go back to x. Okay, we can't leave it like this. All right, any questions on that? Okay, a few more to do. Okay, g of x is equal to the integral from x to x squared, sine of t over t dt. Okay, so we've got this function. Again, a little bit more complicated than last time. For starters, this integrand, finding the antiderivative will be difficult, so we can't do it that way. Here also the lower bound is x, and the upper bound is another function of x. For FTC2, the bottom was a constant and the top was x. We've got a bit of a problem here. But it's not so bad. We can use our definite integral properties. The first thing we're going to do is split this up into two parts so that we can get that constant in the lower bound. So let's write this as the integral from x to 0, sine of t over t dt, plus the integral from 0 to x squared, sine of t dt. So, over t dt. Okay, now this choice of 0 is just arbitrary. You can choose any value there. However, this value, when you substitute it in or you take the limit, it needs to be defined. Okay, if we had, for example, 1 over t and you substitute 0, that's a problem. Here, it's not a problem because we know from L'Hopital's rule that we'll get 1. Okay, so please be careful when you choose this constant. If you substitute the constant in, it should be a nice number. Okay. If it's not, then it's wrong. Okay, so please be careful about this choice. Okay, so we've separated it out. So now we're going to use FTC on each part. The first one, we have an issue because x is at the bottom. X needs to be at the top. We can swap it by putting in a minus sign. Okay, this second part, the x bit is at the top, that's fine, but here it's written as x squared. We don't want that, we want it as a single variable. Let's put u is equal to x squared. And just to remind ourselves, u was x squared. Okay, now, this is still the function. We haven't done the derivative yet. This is still g. So now if we want g prime, we can use FTC2 on each of the terms that we've got there. FTC2 on the first one, that's easy. That's minus sine x over x. On the second one, a little bit more complicated because of the chain rule, but we're going to get sine of u over u, and then du by dx, that's 2x. Okay, we're not done yet because we've still got this u over here, the sine u, and then the u at the bottom. We need to put the x squared back. So finally, g prime of x, that will be minus sine x over x, plus 2x sine of x squared, once we put that back, and then the u is x squared, so we can put that there. Okay, we've got an x at the top and x squared at the bottom. One of those can cancel there. So we can write this as minus sine x over x plus 2 sine x squared over x. Okay, so that is our derivative. Okay, so you see that even if it is complicated like this, where you've got a function of x at the bottom, function of x at the top, once you've split it up, each part is just doing FTC2, right? So the whole thing might be complicated, but if you go through it term by term, it's quite easy. So here, we do the first one, that's done. Then we do the second one, that's done. You might have a third one, you do that one. Each individual one is easy to do. Okay, any questions? Okay, we've got time for one more. And then I'll give you a few more homework problems. Okay, or I don't give you homework problems and you don't get the points. It's fine. Yeah. Sorry? The chain rule part. Sure, I'll do that with this example. So let's say we have g of x is the integral from x squared to x cubed tan of t dt. Okay, so we're going to do this and then I'll go through the chain rule part a bit slower. So here we've got a function of x at the bottom and a function of x at the top. We're going to split it up. Okay, so we've split it up, and just be careful, this point here, 0, if we substitute 0, we don't have any issues there. If we chose something like pi over 2, then that would be a problem. Right, if we put pi over 2, tan pi over 2 goes to infinity, so we can't use that as our choice. But 0, that's fine. Okay, now x squared is at the bottom, we want our x terms to be at the top. Let's swap them. Okay, if we swap them, we need to put that minus sign. Plus the integral from 0 to x cubed, tan of t dt. Okay, now we want to take the derivative. But this top part, the first bit is x squared and the second bit is x cubed. That's not a single variable by itself. We've got a problem. So for the first one, let's say u is equal to x squared for this first bit. For the second bit, let's say w is equal to x cubed. Okay, again, why am I doing that? Because this top part needs to be a variable on its own. X cubed is not a variable on its own. It's a function of x. If I put a w there, then it is a variable on its own. Okay, so that's why I'm making those substitutions. So now we can write this as the integral from 0 to u, again with the minus sign, tan of t dt, plus the integral from 0 to w, tan of t dt. Okay, now we need to take the derivative. Let's look at this first term. We have the integral from 0 to u. So this is a function of u, and u is a function of x. So this first part, this is a function of u, and u is a function of x. Whenever you have that, so whenever you say u, this is a function of u, and u is a function of x, the first thing you should be thinking of is chain rule, because you've got that function composition. So g is a function of u is a function of x. You've got that composition. If you're finding the derivative, you need to use the chain rule. So g is a function of u, and u is a function of x. You've got that composition. If you then want to find the derivative, we need the chain rule. So it will be dg by du, because that's the first bit, and then du by dx, because that's the second bit. dg by du, that's the first bit. du by dx, that's the second bit. Okay, if x was a function of something else, then you would have that third term. Okay, so that's the chain rule. Is that all right? Good. Not good. Yeah, you can say if not good, I'll go through it again. So here, g of u of x. Is that part okay? Yeah, so this top part, we could even write here u is equal to x squared as the upper bound. That's fine as well, if you want to write it like that. So g is a function of u, because that's what we have at the top, and then u is a function of x, because u equals x squared. Okay, so we've got this composition. Let's go down here. Okay, so here is a function composition. Okay, let's do a little side example. So let's say we had sine of x squared. Okay, so we've seen this before. We want to take the derivative. We take the derivative of the outside function, that will be cos. We leave the inside part alone, multiplied by the derivative of the inside part, which is 2x. So all we're doing here is we're saying that this inside part is u. So it will be cos of u, and then du by dx. Okay, so it's exactly the same here. So here, that thing there was u equals x squared. Think of that as sine of x squared. You take the derivative of the outer function using FTC 2, then multiplied by the derivative of the inside function, which is x squared. Okay, so here, let's continue. So g prime, we're going to take the derivative of the outside function, FTC2. So that will be minus tan of u. Okay, that's just FTC2, that's how we take the derivative. But we're not done yet, because we need to take the derivative of the inside function, which is x squared. Right, because it's x squared there. So that will be times 2x. Plus, and then we do the same thing for the next term. So this one was in terms of w, so it's dg by dw, dw dx. So it will be tan w times dw dx. But w was x cubed, so it will be 3x squared. Okay, but we can't leave it like that, because u and w, we introduced that, so we need to go back to x. So this will be minus 2x tan of x squared, just rewriting that, plus 3x squared tan x cubed. Okay, so it's just writing it a bit neatly, with this w being x cubed and the u being x squared. Okay, you good? Okay. Okay, so if you have any issues later on, please just send me an email, or you can come to my office. This will be about as difficult as the tutorials will get. Doing something like this, where you've got a function at the bottom, function at the top, and then you need to split it up. Okay, so for the test, again, this will be as difficult as it gets. Okay, some function at the bottom, some function at the top, and then you need to do the splitting up along with the u substitution. Okay, so here we put the u, you can call it whatever you want, right? Okay, any questions? Okay, so 2 people have provided me with the tutorial already, so they got some points for that. If you do come to my office with your tutorial, just for me to check, I can give you some points as well, but that will be either today or tomorrow, okay, because Wednesday we've got something new to do. Okay, but if you want to come to my office with any other questions, that's fine as well. Okay, and with the homework as well, if you want to come to show me the homework to get your points for that, you can do that as well, today, tomorrow, or sometime before the lecture on Wednesday. Okay, any questions before we go? Okay, cool.